Hi everyone, welcome back to Lab. So this is Lab 5. It'll be on transformations and KDEs. So I read some of your guys' feedback in the feedback form. Thanks to those of you who filled it out. Seems like you guys mostly like these videos. One suggestion was that we split them up into different videos, perhaps for each question or each subpart. I'm going to trial that this time. We'll see. It might end up being in the video, just one long concatenated video anyway. But in this video, I'll try to have like clear, distinct markers. Okay, we're done with question one. Stop. Let's move on to question two. We'll try that this time. So this lab, it's also pretty heavy on text and light on coding. So likewise, it'll be heavy on my words as opposed to me typing. So again, just feel free to skip around and all that sorts of stuff. So the first thing we can do is we can import our autograder as per usual. So in this lab, we'll be plotting and applying data transformations and working with KDEs. So you learned about KDEs in a recent lecture, and you'll get a chance to toy with them in this lab. The data set that we'll be using for this lab, it comes from the World Bank, and it'll have various statistics on different countries, things like literacy rate, gross domestic product, basically your standard like demographic profile of each country, and that's the data set. So as per usual, it's due Thursday night, next Thursday. Here's your collaboration policy again. List any collaborators that you have, and let's get into it. So here we go. We're in our imports here. You see pandas, NumPy. We see a new thing called Seaborn. So I don't think you've seen Seaborn in a lab. Maybe it's come up on a homework. I'm pretty sure you would have seen it in lecture. But Seaborn is basically a wrapper that sits on top of Matplotlib, and it just affords some different functionality. It's all doing Matplotlib under the hood, but it provides a different interface, and I personally like it a lot. So we'll be using Seaborn in this lab. Um, we're using plt.style that basically just sets the style for the plot so they don't look completely basic, and then you don't need to know what any of this means. So let's go ahead and run that, and let's load in the data frame. So you see we're going to be calling it WB. The data set ships with the lab, so you don't need to download it or anything. It just is loaded into your data hub. And we can go ahead and investigate it. We see things like completion rate, literacy rate, access to sanitation facilities, and so on. And there's actually, there's 45 columns here. And it says, this table contains some interesting columns. Let's take a look. And you can see population, GDP, HIV, so a bunch of different statistics about each country. So yeah, that concludes the background portion. All right, so now that we've briefly investigated the data, we can actually get into the content of the lab. So this first part is going to be all about scaling our data and transforming our data. So we're going to be looking at female adult literacy rate, as well as gross national income per capita. So what this code we're going to run here in a minute, it's just basically going to make a new data frame that only has those two columns. And it won't have all this other stuff that is interesting, but we don't care about it for the purposes of this lab. There's a little bit of a note here. It says we're just going to be dropping null values. So for example, if a country doesn't have a female literacy rate listed, we're just not going to be investigating that country. But as you know, that might not always be the best strategy. We're just doing it for the case of simplicity in this lab. Another disclaimer here. Basically, this lab was written, it's slightly out of date. It uses dist plot, basically to plot histograms and density curves. In the past year, I think Seaborn has said, oh, we're going to deprecate this function, and we're going to force you to use dis, no t, displot instead. I don't know why. I don't really like displot. It makes no sense. Like it doesn't, it's harder to work with. We just haven't gotten around to updating this lab yet. So you'll see a bunch of warnings. That's okay. It's just a kind of a consequence of data science being a new and very quick moving field, and people are making changes to these tools all the time. So if you go out in the real world, you'll probably be using displot instead. but in this lab, we'll learn about dist plot. Although kind of the concepts of like knowing how transformations work and knowing how KDEs work, they're the same no matter which of these two methods you use. And you can click these links to check out more. So here's that code that I said we were going to run. We make a new data frame. We give it the same index as the old data frame. And instead of these long annoying titles, we just call it lit and ink. We drop records. We're doing it in place this time. Notice in place equals true. And we can see that we're actually getting rid of about a third of the countries by nature of dropping null values. So again, not best practice, but easiest practice. And that's what we're doing for the purposes of this lab. So you can see some numbers here, Afghanistan 18, Albania 96, so on and so forth. So yeah, maybe these are interesting, maybe they're not. So the first thing we're going to do is we're going to build a histogram of our data to compare we're going to look at the distribution of literacy rates and income per capita. So we're going to be using CountPlot to do this first. So here's some code. We set the figure size. We use subplots here. What this does is it basically says, I want a 1x2 grid, and I want to, like, all the action that I'm about to do below this is going to be on the first of those plots. So I'm going to have two plots side by side, and then, well, I don't know which one is first, but here we're going to be looking at the first one, and all this code is going to be applying to the second one. We could do, if we wanted a 2x2 grid, we could do something like this, and then we could have like two more plots. But basically, this just kind of activates the specific subplot. So this can kind of come in handy if you want to have a bunch of plots on one image. You might do something like this. You can also use AX notation, as I ranted about last week. So here we go. There's a warning. It's taking a while to run. I don't know why. Okay, so here we go. Here's the plots. This code was given to us, by the way. And I didn't do anything here. And like, what the heck is going on? I see it's colorful, nice rainbow color scheme, but I can't really see anything. All the labels are all scrunched together. They make no sense. Zero, like I can't read. Like the titles, like the labels are cool, but like I can't interpret anything. Like I don't know what each of these little bars means. This plot makes no sense. So task for you guys is to explain why CountPlot is not the right tool. And the answer here is that we're working with continuous data. And CountPlot, it makes sense if you only have a few select values. Your data is discrete. Maybe you're looking at like shoe sizes or something, or ages, and everyone's like rounded down to their integer age. Then a CountPlot might work. But for this question, when we have like these continuous values, you get garbage like this. So you can say CountPlot doesn't work for continuous data, which is what we have. Just something basic like that. So now 1b, instead what we're going to do is we're going to use the distplot function, and that'll make a histogram, which will be a lot more useful than a CountPlot. So as above, we should have two subplots, so side by side, literacy on the left, income on the right. So that's exactly what they had up here. And yeah, we're setting the KDE parameter to false. So it literally says hint to copy and paste from above. So that's what I'm going to do. And I'm just going to replace all instances of CountPlot with distplot. And I think that might do it. Again, I see warnings. But now I see, oops, I forgot to do what the question told me to do. And I have to say KDE equals false. So I do this, and it runs, it takes forever. And now I see some nice histograms. And this is a lot more intuitive. It's a lot more readable, understandable than anything than what we saw before. Like this makes no sense. This makes some sense. So I can see that female adult literacy rates, it's skewed left. It's kind of a bit confusing, but skew left means there's lots of data on the right. So we have lots of data on the right, lots of literacy rates are close to 100, that's good. Gross national income per capita, it's skewed right, meaning the tail is pointing right, and there's lots of data on the left. And this is skewed right. There's a lot of national incomes that are pretty small, and that's not so good. So here we go. How are the bins created? We didn't explicitly set bins, and basically it uses this fancy heuristic. It's actually kind of interesting. I should look this up. But of course, if you don't like these bins, maybe you like round numbers instead, like I do. You could set them yourself, but we're not going to bother. So now we're going to do the same thing from before. I guess you could have just copied this code up above. But we're going to set the rug parameter to be true. So rug is just another parameter you can pass into distplot. See another warning. And now you see you have kind of the similar information before, but we can truly see how like the distribution of our data. So we see over here, there's tons and tons of points down here near the left. Over here, it's a little bit more spread out, but you can see each little tick mark represents a data point. So obviously there's a lot more data points in this region than there are in any region over here. So yeah, that's just something you can do. You can set rug equal to true, and that's what you get. And then what are we doing here? We're setting KDE equal to true. And now you see, I kind of did it accidentally before, but now you see a KDE curve. This is, yeah, kernel density estimate. This is an estimate of the continuous distribution curve based on the histogram. So the histogram, like each point, like we only have so many points. Basically, like imagine this rug plot, like just individual, just like literally points. But what we can do is we can kind of give each point a kernel and then produce this estimate like this. So we'll talk more about that later. Another thing to notice is that the axis labels have changed from count to density. I think this came up, I think homework 2 maybe, homework 1. Basically, we're not looking at raw counts anymore. Now the scale is density, because as we know with a density curve, the area underneath this curve has to be 1. So it doesn't make any sense if you have like 150 countries, like it doesn't make sense to have your scale be like go up to like 100 or 150. This just scales things such that our density curve sums to 1. Another thing to point out is that it doesn't really make any sense for an adult literacy rate to be above 100 or a gross national income per capita to be below 0. And that's just a consequence of the KDE function that we're using here. Like no one, like it's not possible to be like in this region over here or this region over here, but that's just how the KDE curve was generated. Just something to keep in mind, kind of like a flaw or just something to be aware of with KDEs. Okay, so now we're going to look specifically at the income data, and we can see, well, we know a lot of countries have low income, but we can't really differentiate them. They're all just kind of clustered over there. They're all less than 20,000, but that's not really saying a lot, are they? Is it 50? Is it 500? Is it 5,000? We can't really tell. We just know that there's a lot of them close to 0. So what we're going to do is we're going to transform this data using a transformation. So yeah, we're going to do a log transformation. And that's because if our data is skewed right, a log transformation is a good idea. Why is it a good idea? Because logs generally make things smaller. And that effect is more pronounced the larger your point is. So basically these points way out here, they're going to be kind of brought in together down with the rest of these points, if that makes sense. Log, because log, you can kind of see it goes like this. So it increases, but it increases slowly. So I guess it was the opposite. It's less pronounced the larger you are. So it'll bring, well, it's really, yeah, forget everything I just said about more or less pronounced. But basically what's going to happen is it makes large values pretty small. Whereas over here, we don't want to do a log transformation. That'll just exacerbate things. We might use like a power transformation instead, because a power transformation is going to make small values big. Anyway, so we're going to do a log transformation here. It's nice because the summary statistics like the mean and standard deviation, they're more stable once we have a symmetric distribution. So yeah, let's do that. We're going to make a plot of ink with the data transformed using np.log10. And you can set the KDE parameter to be whatever you want. So I'll go ahead and I'll just copy this. And instead of df ink being my data, remember this is a series, so I can do whatever operations on it and it'll do operations on the whole series. So I can say np.log10 that. And I think this should do it. And now you see it looks a lot more symmetric. It's not perfectly symmetric. There's a little bit of a plateau kind of over here, but it's definitely more symmetric than what we had before. And you can see the rug plot again. You can see the KDE curve. We don't have raw counts because I set KDE equal to true. But this is a lot we can get a better sense of what's going on here. What are these numbers down here? Well, it's the log of the gross national income per capita. So it's this would be 10 squared, so 100, 10 cubed, so 1,000, and so on, as opposed to the linear scale that we saw in the previous parts. So yeah, if a distribution has a long right tail, log's generally a good idea, as I stumbled over a few minutes ago. So we can do a similar thing for literacy. So literacy, remember, is skewed left. It has a left tail. So we can do a power transformation, for example, to the 4th power. And we can see what that looks like. And you can see it's still not really symmetric. There's it's like bimodal almost. But it's definitely more even, more spread out than what we saw up here. So you can toy around with other numbers. Let's say, I don't know, 3, 2. You can see 2 doesn't really do a whole lot. It's still heavily skewed to the left, skewed left. But if we do 4, then it's a little bit better. To the 4th power. And what kind of distributions have left tails? Well, when there's a maximum. So for example, a percentage. You can't go higher than 100. GPAs can't really be higher than 4 in college anyway. Okay, so that's that. Now we can move on to 1D. We want to examine the relationship between female adult literacy rate and gross national income per capita. We're going to make a scatter plot. So instead of just looking at side-by-side histograms, we're going to make a scatter plot. And we're going to use sns.scatterplot. So we can say sns.scatterplot. We can say x equals literacy rate. So let's say df lit, y equals df inc. Let's set that to x. And you can see a scatter plot. It's not super, there's definitely overplotting here. This could definitely benefit from a transformation or two. We see all the points are kind of down here. They're congested over here. Basically, this whole space in the plot is empty. So ideally, we would use a transformation here. We're told not to. But yeah, I think you can, if you want to make the dots smaller, you can make the size. That's really small. But you can set the S parameter to make the point smaller. So maybe something like 10. Maybe that reduces the overplotting a little bit. Make sure we label both axes. So we can say plot.x label. I'll just copy these. I couldn't be bothered to type all that up. So we want plot.x label, plot.y label, and then plot.title, income and literacy rate. And then you see, I mean, it's kind of crummy looking. Maybe we should shorten one of these labels, but there you go. Just basically, the point here, literally just make the scatter plot using sns.scatterplot. Okay, so now what we're going to do is we are going to do a transformation. So here we're doing the same thing as before, but we're taking the log of income. So instead of linear, like raw income over here on the left, now we're going to have the log of income. And now you can see it's a little bit better. There's a lot of points still congested over here. Maybe we could do another transformation of the x variable, but this is definitely more of a linear relationship, more of a like easier relationship to see than this plot. So yeah, what do we do now? Now we're going to square literacy and take the log of income. So kind of just what I alluded to before. We're actually going to do great, awesome. We're going to square literacy. And then let's say, yeah. And now you see, it looks basically the same. It's not the same. But you can see the points that were bunched together here, they're slightly less bunched together, and things are more spread out. So yeah, how do we interpret these plots? Well, once you kind of start fudging with the transformations, it's a little bit harder to interpret. But for example, this plot, basically we say that one increase, like one additional percentage point for literacy rate, that corresponds to a 1% change, or whatever the slope is, such and such percent change in the response variable in y, which in this case is national income. So yeah, that concludes part 1, question 1. Yeah, I'll be back in a second. Okay, so now we're back with question 2. In this one, we'll discuss KDEs a lot better. So what is a KDE? Well, it's using to estimate the probability density function. So you've seen like the classic bell curve, like the Gaussian distribution. You've seen probably, hopefully, a bunch of other distributions. And the KDE is a way of estimating what that curve actually looks like. So what we're going to do is for each observation, you place a kernel. And what is a kernel? Well, a kernel is some function based on the input point, and then it draws some kind of curve or a line across all values of x. So your point x is literally just a point. It doesn't have any like width, but basically a kernel gives your point some width. I think honestly, maybe you could interchange 2 and 3, but basically what we're going to do is for each point, we have one of these curves. We're going to add them all together, just like stack all of them on top of each other, so to speak, and then normalize them such that they sum to 1. So here it says normalize first. I guess like either way, it doesn't matter as long as you normalize in general, but we need to normalize and sum. So there's a bunch of stuff you need to consider when making a kernel. You need to choose the function. Do you want a Gaussian kernel? Do you want a boxcar kernel? Do you want some other kernel that we haven't discussed in this class? We need a bandwidth parameter. So that's how wide we want our kernel to be. Do we want our kernel to be kind of very tight around the point, or do we want it to be much more spread out around the point? That's something you need to decide just as a data scientist. Yeah. So let's say we have 3 data points, 2, 4, and 9. So I'll make a histogram. So for some reason, I guess 2 and 4 are in this bar, in this bin. 9 is in this bin. So yeah, not really exciting. What we can do is we can generate a KDE of the data. So now we have our histogram again, the same histogram as before. And now it's drawing a nice density curve using some density function. It just says KDE. We don't know like the settings of that. It's kind of black boxy, but it's drawing a density curve. Okay, well, it's black boxy, so let's make it not black boxy. How does it know how wide each point should be? Like, how does it know to give it this much width? Why is it not like a lot more narrow, something like that? So what we can do is we can set the bandwidth parameter called BW in Seaborn, and we can just set that. So if we set it to say 0.5, we get something that looks pretty different. It is a lot more narrow. Each point definitely has its own noticeable, like each point is a lot more noticeable here than it is up here. And you can try different values. Let's see what happens if I set 0.1. Well, then now you can really see the difference. If I set, say, like 10, then it's just like one long flat line, and you can see like it goes from -50 to 50. So maybe 10 isn't the best idea, but you can just toy around with these and just explore the different results. So now let's go into a question. We're going to build our own KDE from scratch. So here's the function. It's basically the normal curve. Pretty nasty math. EXP means e to the power. So here's the function, and here's the function in Python. So alpha is called the bandwidth parameter, so that determines how wide our kernel should be. A larger alpha means more wide. Smaller alpha means more narrow. So we have alpha. You can see alpha in here. We have x. So x is the center. X is the point, so that'll be the center of our kernel. Wrong. Sorry. Z is the center of our kernel. So Z is the point that we're passing in. And then X is, at a given value of X, what is the kernel? What is the value of the kernel, which is centered at Z? That's what that means. So yeah, I got them flipped. But Z is the center, and X is just a point along the X-axis. Okay, run the function. We can plot the Gaussian kernel centered at 9 with alpha equals 0.5. So let's say we say alpha equals 0.5. Here's what the kernel looks like specifically for 0.9. Remember, we have 3 points, 2, 4, and 9. And here's what it looks like for 9. So now what we're going to do in this problem is we're just going to do it for all 3 of them. So, okay, here's some hints. Basically, just draw all 3 side by side. We can start with copying this code. As is the standard for labs, copying code. So we have alpha, x, and 9. And it says the Gaussian kernel function can also take a numpy array as an argument for z. So sounds like I want to make an array. np.array with our 3 points, 2, 4, and 9. To plot multiple points at once, you can use plot.plot x as y with a 2D array as y. Well, let's just run this and see. I'm kind of curious. It works right away. I wasn't necessarily expecting that, but there you go. So now we see 3 different curves. We see one curve is definitely centered at 2, another at 4, the last one at 9, and they're all just plotted side by side. One thing I forgot to do is I forgot to normalize. So remember, we need to multiply by 1/3. Oops. To make sure that the total sum is 1. Each individual point, so for example, the area under the green curve has to be 1/3. So that when we add all 3 of these together, they sum to 1. Okay. So this plot is given to us, and it shows us the sum of the 3 things with bandwidth 0.5. Okay, so now you see them all stacked together. So here's what the KDE of the log of the income. So going back to the previous part with the log data. Yeah, there's the KDE, just using sns.dispplot. So now what we're going to do is shown what was done in 2a, try different values of alpha. So this is basically just using our function that we wrote before to kind of recreate this. So like try and like kind of I forget what the word is, but kind of reverse engineer what alpha parameter they used here. So now we're trying it with 0.1. It looks like this, kind of similar. Maybe we can try 0.5. That's very smooth, so probably not that. And it says, well, if you use alpha equals 0.2, it'll match the graph well. So not perfectly, but pretty similar. They used something close to 0.2. Okay, that's part A. So now for part B, it said, hey, you hard code a lot of your work. Hard coding bad. Don't hard code. We're just going to build a KDE from scratch, or in general. So this KDE function, it'll compute the KDE for a given value of x, so remember x is a point along this axis, you can imagine if we have f of x, this blue curve is literally f of x. So for each, what we're going to do is the value of f, the value of the KDE at point x, is equal to the average kernel across all of the points for that value x. So this is kind of confusing, but basically we have a sum here from I equals 1 to n, zi. So basically z is our data. So for each point, we're going to get a different value of k of our kernel. Each point has its own kernel. Hopefully that's clear by now. And then what we're going to do is we're going to sum and then normalize. So that way we get an aggregate kernel like this. K, what is k? Well, k is just an arbitrary kernel function. So up here we wrote, or they gave to us a specific type of k called the Gaussian kernel, which has this formula. But k doesn't have to be that. K can be something completely different. So this function that we're going to write allows us to use arbitrary k. Okay. So what do we need to do? Well, the first thing we need to do is we need to find the value of the kernel at point x. Kernel takes in 3 parameters. So alpha is the first parameter. And then, so it literally tells us kernel takes in alpha x in data. So we can do that. Awesome. We need to do that. And then we need to find the average. And I'm pretty sure this is all that we need to do. Remember, kernel is a function, but we can pass it in as its own function. Higher order functions, 61A, everyone's favorite. Yeah. So here, yeah, kernel is a function such as Gaussian kernel, which was written earlier. So yeah, I think this is straightforward. Obviously, we need to return. Do we pass the test cases? Yes, we do. Awesome. So assuming this works, which it does, we pass the test cases. We can generate the KDE, the log of income from before. I don't know why it's orange all of a sudden, but you can see here's the log of income with alpha equal to 0.2 or whatever it was up above. Okay, and what this is going to do is this is going to show us a 3x3 set of plots. So it'll just show us a bunch of different alphas. And I don't know why this is taking forever to run, but it's doing a lot of KDE processing. Here we go. Okay, so now you can see. I'm pretty sure this is just alpha. Like the only thing changing here is alpha. Maybe the starter code could have included some labels. But yeah, basically we have a bunch of different alphas going from 0.2 to 2, and then we just plot the KDEs for each of the alphas. So 0.2, 0.4, 0.6, and so on. And you can see they're definitely getting smoother and smoother. I guess if alpha was infinite, then you'd literally just get like a flat straight line. So yeah. So I alluded to before, we don't need to use the Gaussian kernel. There's nothing stopping us. Like we can just use any kernel we want. And another type of kernel is called the boxcar kernel. And here's the formula. I think you've seen it in lecture, but here's the formula in code. It looks kind of gibberish. You don't really need to know how it works. Maybe we could throw some parentheses in there, but whatever, it's beside the point. So what this is going to do is we're going to run some interactive plots. So here we go. So here's what's our data here? This is just showing what they look like for a specific point. So if I had alpha equals 5, that's what it looked like to start. If I decrease alpha, you can see they're both getting narrower. If I decrease it again, they get narrower. If I make it really big, they get hella wide. So yeah. Now what we're going to do is we're actually going to plot this on the log on the data. So this is going to be very slow responsive, so I'm not going to spend a whole lot of time on it. But you can see alpha G represents the alpha for the Gaussian kernel. Alpha B represents the alpha for the boxcar kernel. And you can see the boxcar kernel, it's a lot more jaggedy. And that's just the consequence of how it's created. But I can see I can make it a lot, if I make it smaller, you can see it getting wider. What's the question? Briefly compare and contrast. How do the kernels relate to each other with the same alpha value? Well, let's try. Let's set alpha g to be 0.5 because apparently that's as high as it goes. And we can set alpha b to be 0.5. It'll take very long to update. And you can see while it's updating that Boxcar is less smooth, more jaggedy for the same alpha. And you can be fancy and you can put LaTeX. Yeah. And Gaussian. So yeah, just something like that. Toy around with these. It's pretty interesting. And yeah, that's it. So let's just check all. There's one test, so hopefully you passed it. And then we export and submit to Gradescope and you're good to go. So yeah, that's Lab 5. Hope you enjoyed it.